Okay, today we're going to talk about closed loop HST systems. Closed loop HST systems. So essentially, closed loop HST system is where all the pump flow goes straight to the motor, and it does not go back to tank. It goes straight back to the pump. So what comes out of the pump goes to the motor, what comes out of the motor goes back to the pump. That's a closed loop situation. There's no DCB in front of the motor or between the pump and the motor to direct the oil flow to go either in work port A or work port B of the motor. It is straight out of one side of the pump, straight into the motor. Whatever comes out of the motor should go back to the pump. So here's what we need to do. We need to build ourselves a variable displacement pump to begin with. So I'll just start over here and give you a little rundown. I give myself a variable displacement pump pretty soon. By pump, we'll throw some energy arrow out of it so that I can have some energy coming out of it. And if I come out, then I will run somewhere over hereabouts and come down into a motor. All right, well, then I need a motor. Something like that. And we should have some energy going into it. Life is good. And if we got energy going into it, then it should possibly turn something. All right, let's try and turn something that direction, providing the oil can actually get out of it. So we need some passage for the oil to come out of it to get right back to our pump. And this is essentially a closed loop. If, and I probably need to have some oil flow, so I'll just make it deliver oil out of it to go over to a motor, which will take the oil and get back into it. So that's the start of our closed loop system. So I'm going to help this out a little bit. One thing, in order to do this, I'm going to say that I probably need to be variable. And that is to say this pump that is going to be producing will go from true 0 degrees. So neutral is actually true 0 degrees. That's neutral. Now, as far as this is, forward on this, to make this thing turn clockwise over there, I'll just call that forward. This might be anywhere from 0, no, it's got to have some flow coming out of it, so it's 0.1 degree or 1 degree up to a maximum of, say, maybe 20 degrees is what I'm going to use as an example. Most of the ones I worked at were around 18 degrees as a maximum swash plate angle, but we'll use this one as 20 degrees, maximum 20 degrees. So this will go from true 0 all the way up to about 20 degrees, producing a variable flow, which will make this turn either slightly slow, just moving, and the more my swash plate angle is, the faster my motor is. And that works fine, and I can get forward direction out of that. How this works in this closed loop system is I also maybe want to have some means to make it go the other direction. So we'll just make this an energy arrow either direction now. And I'm going to call this reverse. So now this is reverse. I don't know if you can see that, but it should be reverse. And that is about 20 degrees as well, infinitely variable on my swash plate angle. And that will produce flow out the pump this other way in this closed loop, sending energy in to my motor, and it will drive it the opposite direction, being reverse, infinitely variable versus forward, infinitely variable. And this is the closed loop concept to start off with. We just got variable, infinitely variable pump providing flow to our motor, which goes back to the pump, which goes back to the motor, and it's a closed loop design. There's a couple of things missing off of this that we should be well aware of by now. And one of the things that's missing off this might be this thing, which I'll draw like so, way down here for a reason, because I'm going to put something in here eventually. So I just draw that like down there, and we say, oh, the motor's got a K-string on it. We've seen it before, we know it's there. And besides that, off the top of this pump, and I can't go too far because it'll be out of view. So off of this top of this pump, I'll run this, and I'll put a K-string on it as well. So now I've got a K-string on the pump, and I got a K-string on the motor. So all of a sudden, my closed loop system has a problem. And if we're not sure what the problem is, and I'm just going to drive with the fancy little motor over here. I'm just going to drive this mechanical connection for this motor. There's a problem here though. So this is a closed loop design. What comes out goes in, and it comes out, goes in, and so on and so forth, except how do I make up for the loss of oil in this closed loop? Where's the hydraulic tank? Because all it takes is for me to lose a half a drop of oil, and I cavitate my really expensive variable piston pump, and it's like, oh no, life is bad. So here's what we got to do. We got to build a couple of scenarios. We got to build some way to replenish this. That would be one thing we got to do. So I got to add to it, but I'm going to make sure I protect that pump in a different way first, because even before I've starved it from cavitation, what would happen if I pushed this thing into forward? And this is going to be set by the operator. This is not an automated system. This is operator dictates this angle. So what would happen if I push this forward and for some reason I did this to the motor so that the motor wouldn't rotate? So right now, if I ask the pump to produce 50 gallons a minute and all of a sudden that motor won't rotate, this is not automated. This is operator selected. And all that pump flow's got to go someplace. Things would blow up. So I better put something in here to protect this thing before I get onto the whole starved of oil possibility. I better put something in to protect this thing from what? Overpressurizing while I'm going forward. So here's what I'm going to do. I'm going to put this in. And this is nothing more than a normally closed valve that might be adjustable. That sound fair? And here's what I'm going to do to that. I'm just going to connect it to here. And I'm even going to sense upstream of the valve physically to open it. If I ask it to produce flow and that doesn't go anywhere, if I was to actually put, I don't know, a pressure gauge on the top of here, that pressure gauge, based off of resistance and the motor won't turn, that pressure gauge goes up, 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 until, I'll give this a number, 8,000 PSI. Then that valve opens, and when it opens, it goes right back to the other side of that closed loop. So now, if that won't turn, then the oil builds up enough pressure till I see whatever it takes to overcome that. And in this case, 8,000 PSI. This valve would open, allowing the oil to go to the other side, which would be, and now my closed loop is essentially over this relief valve. Round and round and round we go. And I protect this closed loop on this side from overpressurizing. In other words, we don't blow anything up. But if I was to go in reverse, if I go in reverse, then 50 gallons a minute, maybe trying to go this way, and if I still can't turn that, wait a minute, I have no way to sense whatever this pressure is here. Whatever that pressure is, I have no way to sense it. So this valve would just stay closed. So really what I'm trying to tell you is that works for one direction, but I need another one for the other side to go in reverse side. So if I'm going reverse, I need to protect reverse from overpressurizing. So what I'm going to do is, oh, I don't know, I might just throw in another valve that for all practical purposes, and I need a little space, so I put this spring on the inside, and I'll put the exact same spring force on here, and I'll just now, for all practical purposes, I'll connect this one on here, and I'll sense upstream of that, and when it opens, it will drop to the unloaded side, the side that's actually pulling in oil out of this pump. It's producing oil flow this way, trying to turn that motor. It's not my fault. There's something preventing me from turning that motor. So I don't blow things up. The pressure gauge climbs until it opens up this high pressure relief valve. 8,000 PSI is not unheard of. I just used 8,000, but it's not unheard of. So it opens up this high pressure relief, then dumping to the other side. There is no resistance. This is actually pulling in, drawing in oil in this loop. So on the other side of this relief valve, there should be zero, initially, zero. And the reality of it is zero, in fact, becomes vacuum because of this internal leak problem that we still need to fix. And I'm gonna just modify something at the moment. I'm gonna put a pressure gauge over here on the red loop because I think you can see it better. So I'm just gonna put, theoretically, this would be vacuum on the other side of that because of this internal leakage. This is the oil that's being forced out. Meanwhile, the other side of the relief valve right here is the same as what's being pulled or drawn into the pump, except the pump has got internal leakage out of it. So this closed loop is now really got problems, because in a closed loop, if you lose a half a drop of oil, you've starved something. Something is cavitated. So what we need to do is we need to build some means to make sure that this really expensive pump comes with always some kind of charged pressure on the inlet of that pump. So let's build something that protects it, and let's make sure that this pump, this big, expensive, doing a lot of work for us pump, it always has some kind of charge pressure on it. So why don't we put, I don't know, let's put a charge pump on. So here's what I'm going to do. I'm going to put a little mechanical drive on this big pump, and I'm going to put, for all practical purposes, I'm going to put another little pump on here, and we're going to take some flow out of it. So I'll just take some flow out of this. It's going to produce flow, so it's got to draw it from someplace. Guess what? I'm going to pull it out of the tank. This case drains are going to the tank ultimately, so I'm going to pull the oil out of the tank, and in our scenario that we just finished with, we needed to keep this replenished. I wanted to make sure that any oil was going into here, so here's what I'm going to do. I'm going to allow it to go into this side right now and make sure, technically not correct yet, but I'll make sure that this oil flow is always going in. It's producing enough oil to put oil into here to make up for the leakage. But I could be losing 1 drop, or I could be losing a half a gallon. And this pump is just producing enough to keep up with leakage. I'm going to suggest to you this pump is producing, I don't know, a few gallons worth. And it might be these are brand new and there's only a couple drops there and a couple drops there. That would be bad. Because now this pump is producing enough more flow than what the leakage is, and that would overpressurize the loop, even on the unloaded side, and blow out the seals out of my pump, or motor, or both. So there's all kinds of problems that come out of this, so I'll tell you what I'll do. I'll prevent this pressure from going too high, yet I'll make sure that it maintains a minimum amount of pressure. So here's what I'm going to do. I'm going to put another valve in this thing. Right here, another normally closed valve. And I'm going to put a spring on it, a little adjustable spring on it, and a normally closed valve, you say. A normally closed valve that allows oil to either go this way into that loop or this way into it. And if it opens, then I can send it into here, knowing that ultimately that oil is coming out of this case drain going back to tank anyway. So here's a valve that's normally closed. I need some way to open it. Going back to tank, probably no pressure downstream of the valve, so I'm going to sense upstream of the valve to physically open that valve. And I'm going to create, I can go that way or that way. So whatever I set this to will limit the maximum pressure I see in there. So I'll tell you what. We're going to pre-charge this, I don't know, 400 PSI. That's a fairly realistic number. So I'm going to pre-charge this to 400 PSI. So what I would see here, over here now, would be the 400 PSI, despite the fact my motor won't turn. I build up to 8,000 on this side. I open up the relief. I'm going in this closed loop, but I'm still trying to make up for this case drain internal leakage for lubrication and cooling. So instead of seeing 0 or less than 0, even a vacuum to cavity, it's actually this charge pump is charging the unloaded side of this loop to 400 PSI, and so it's drawing in oil at 400 PSI, which is charging the inlet for this expensive pump. So the pump is protected in reverse. But, and I said there's a few pieces missing, and technically not correct yet. So here's what really goes on. I'll go one step further, of course. I wanted to throw it into forward now, to try and turn that wheel. But if I throw it into forward, then if that motor isn't turning and the oil out of this pump can come out and just go through this little 400 PSI, I certainly can't get to maximum force on my motor and see 8,000. So I need to isolate my high pressure, do some work loop away from my, what I refer to as the charge pump for the control side for all the little stuff. So the easiest way I can isolate that for all practical purposes is with this isolation check valve. So I can isolate it so that it can feed in when I want, but not that it can take this pump flow and go that way. So now if I throw this in forward and that motor doesn't want to turn because there's a lot of resistance, I will build up enough pressure until can't go anywhere, can't go anywhere, can't go anywhere. Oh, I can sense this, and I will overcome that spring. What is that spring set on? 8,000 PSI on this side. And I go to the other side and, oh, shoot. Now I'm back to the case drain issue that I need to replenish. So I would have a vacuum on this side because of that little leakage I got to keep up with. So here's what I'm going to do. I'm going to connect this charge pump to the other side that is now on the unloaded side and isolate the unloaded side with this lovely little check ball. And then I'm going to connect that so that when it wants to, when it physically wants to, 8,000 on that side, can't go anywhere, opens up that, I'm on this side. Really, this side will always see, theoretically, back to that 400 PSI. Now this is a starting step, so again, this is not quite technically correct, but this is how we start. And that is to say, I have now got a closed loop system where all of my main pump flow is going to drive that motor, and I put in some means to protect it in driving it either one direction or the other direction. And I've also put in a system here where I can make sure that the unloaded side of this closed loop is always going to see some kind of a pre-charge pressure, regardless of whether that's loaded or not. So I got to show you what happens when it's not loaded. But that is to say, if there's resistance to turn and it won't turn the motor and the pump's producing flow, it still has to go somewhere. It goes over this high pressure relief valve, and then it comes down to this side, and this charge pump is making sure that this unloaded side after the relief is still at 400 PSI. That's kind of the stepping stone, protecting this pump. That's that charge pump's job, amongst so many others that we're going to show and talk about here in the next 20 minutes or so. So that's kind of the stepping stone of it. And the only thing I want to be rest assured about is that's going to produce a lot of heat first and foremost. But I want to be clear on a few things right here, right now. First, I'm telling you what I'm going to do. I'm going to make this thing go to true neutral degrees. And that is, there's no flow this way and there's no flow that way out of this pump. Which means, as far as what that means no flow out of either one of these loops. So I would ask you how much pressure is actually on A and how much pressure is on B if there's no flow coming out of the pump to try and drive the motor. Even though the brake's on the motor, there's no flow coming out of the pump. So what would my pressure on A or B? B? Oh, bad pun. So give you a second to think about it, and the reality of the answer is, what's dictating the pressure in this loop? This charge pump is still producing flow into this loop, either side. And by either side, the path of least resistance. So even though there's leakage out of this case of this pump and that motor, A and B will still see 400 PSI on each of these. And I refer to this as, for all practical purposes, this is neutral charge pressure. And yes, I should write slower. But that's neutral charge pressure. That means that pump is ready to go. I got a high pressure loop that's sitting there waiting to do something, and I got a low pressure loop, or I have a low pressure system making sure the high pressure loop is ready to go. So there's a few more things missing now that we got to throw into that. And that is to say, I refer to this as a neutral charge pressure because that is very, very true. What happens is we have to build some means to cool this thing. So here's what I'm going to do. I'm going to go over here, and coming out of this lovely motor, this is what I'm going to do. I'm going to throw this in this motor. And that is to say, I need to cool this oil down at some point in my life. Well, where are you going to get the oil from? All you got is a measly little K-string. I think we can make something. Let's design something into this. Let's throw another couple of valves in here that actually can help us with the cooling. So here's another valve. We'll throw another valve in, see how I do. I need a valve for all practical purposes. 3 envelopes. I need a valve. And I can even spring center it for you. I need a valve like so. And I need a valve like so, and a valve like so, and that's a good start. And now we need to add some colors. So, here's what I got going on. Red is going to connect up here, and I'm going to take a red energy arrow in here to physically pilot that valve to move it down, to shuttle it to what I referred to as really this envelope on this side. Okay, and that is to say on the other side of this valve, we're also going to connect it to this side of that high pressure loop, and we're going to sense that to shuttle it the other direction and use this side of the loop now. So here's what actually goes on inside of it. If I shuttle it down that way, I'm actually going to take this oil and send it somewhere at the moment, making sure that this stays blocked. And if I shuttle it down this way, I will take this side of the oil, making sure that this side stays blocked. And the question is, what do I do with the oil? Well, the oil that comes out of here is really going to another valve, or it could just be a variable orifice, but I'll draw it as a valve because it seems to work better as a valve, so why wouldn't I draw it that way? And I think we should be able to dictate from this that here's a valve that is normally closed in comparison to the lines that line up with it and the lines that run out of it. I need some way to open that valve, and it's going to be sensed upstream of the valve again. Physically open that valve up when the time is right. That seems logical to me. Okay, so if I open that valve in the right scenario, it will dump into this motor housing, which ultimately comes into this motor housing and mixes with the motor drain, ultimately cooling off, and therefore going back to tank. Tank, which I pull out of here cold. Oh. Okay, so now I got a means to get oil into there. I just have to figure out how this valve all works that I've drawn in here so weirdly. So, 2 high pressure loops, 1 for either direction for this particular pump and motor closed loop. This is known as a flushing valve, which is utilized for cooling. Okay, and we're going to make sure, let's see how this actually operates. So first in true zero, I have 400 on one side, 400 on the other, and 400 on one side, 400 on the other. I can pretty much say that these closed loops, this closed loop oil flow is blocked. So there's no oil that is going to this for cooling other than just the internal leakage in this particular motor at this point. I could even take the case drain from this pump and run it all the way over into this as well, and that's what they often do. But I just left it over here for this drawing. So right now in neutral, it's not cooling itself. However, when we are in, and I'll just say maximum forward because we've already used maximum forward and this is still blocked. When we're in maximum forward, then pump flow is starting to go someplace. If it won't turn that motor, it's going to demand, I'm going to ask for 50 gallons a minute, and that 50 gallons a minute is going to try and go this way. It's going to try and push this down, which is to use this particular envelope now. It's going to push this down, which still blocks off the red port in this envelope, opens up the blue port, but it blocks the red port, so all of this pump flow can't go that way, can't go that way, can't go this way, and can't go here. It's forced to open up that relief valve. So I would see 8,000 PSI capabilities up here. And on the unloaded side that's supposed to be charging this now, I open up the blue port over here. I open up this side to this valve, which actually opens at 350 PSI. Instead of the original 400 that was in this loop, now this loop is open to 350 PSI. So I open this up because 350 will move before 400, and I will open this up now to 350 PSI, and now my oil is being cooled. So when I really need it, when I'm working it, all of a sudden, when I got more pressure on one side, this particular flushing valve will shuttle up or down, and it will take the oil flow from the unloaded side of this loop to cool. Therefore, making sure that all of the pump flow is going to the motor to turn the motor. That's its job. The charge pump is making sure we pre-charge the pump, the main pump, as well as now providing the oil flow for cooling as well as pre-charging. And it's pre-charged at 50 PSI less than what my neutral charge pressure is. 350 PSI is more than enough still to protect that fancy expensive piston pump. So let it be. And I refer to, this is definitely my flushing valve. I refer to this as my operational charge relief valve. And it's located right on the motor, just like this flushing valve is located on the motor, whereas these high pressure reliefs are located right close to this main pump usually. This flushing valve and this operational charge relief is actually right on the motor. Some modules will call it an operational charge relief, and some modules will call it the flushing valve relief. Depends on the module you read. I prefer to look at it as my operational charge because it really is setting my operational charge. That's just how my mind thinks. And if I was testing it, I would know that in neutral, my charge pressure should be in those loops about 400 PSI. And as soon as I move, and even if this is rotating with minimal resistance, 1,000 PSI, minimal resistance, really that's still 1,000 PSI on this way versus what would have been 400. It's enough to shuttle it down and you're already into cooling mode, and that still drops down to about 350 PSI. So I know that operational charge relief or the flushing relief, depending on which module you read, I know that it's working, and I know the oil is cooling when my charge pressure drops down a little bit when you start operating. So that's why, like, there are two distinctively different systems here. There is a high pressure pump and motor, big, and a high pressure relief trying to do some work. And then there's the charge pump protecting this pump, making sure that it's good to go. And there's this neutral charge relief, and there's a flushing valve for cooling. Oh, cooling rate. And so now the charge pump is providing the oil flow for cooling as well. And that's kind of what's going on with the pump and the two systems in this closed loop system. So back to neutral, I would see right back to the original. In neutral, one pressure is the same as the other. The flushing valve is neutralized, and my loops will then set right back on 400 psi each. That's the scenario. And that's almost all you need to know. As far as what goes on in this system, if I was to put a hydraulic filter into it, and this is what's in your modules, if I was to put a hydraulic filter into it, I would probably put that filter right in here, and maybe a filter bypass around it as well. Of course I would, but that's where it's located. Why would you put a high pressure filter in 8,000 psi, need a big housing, when I've got only 400 here? So now the charge circuit is actually where I filtrate the oil as well. And I could put the filter way back over there as it returns the tank. I could do that. There's more room over here. I could put a filter in, well, I'll put a filter in here, just why not? Because you asked for it. So I'll put a filter in there, and that's fine. I happen to have the room, so why don't I put a filter bypass in as well? Something like that. So now there's a filter and a filter bypass. Oh yeah, that's fine. Now my charge pump is actually filtering the oil and allowing it to bypass. So now we've looked at all the different things that charge pump. Yeah, making sure the main pump is good to go. Making sure there's charge pump pressure. Good for cooling. Good for filtration. And what we don't see yet, and what is in your module, is this swash plate angle, which I said was, for all practical purposes, I said it was operator dictates whether I want forward or whether I want reverse on a mechanical lever. But we could actually use, for all practical purposes, we could use this charge pump to run to, I don't know, for all practical purposes, we could use this charge pump to run to a DCB that, something like that, where I could dictate that I actually want to go to an actuator. An actuator one direction or an actuator the other direction. I mean, ultimately I can send oil in either one direction or the other direction with a DCB to control my swash plate angle. So this becomes operator input. And again, the charge pump is providing the oil to control my main pump's infinitely variable swash plate angle from true zero all the way up to about 20 degrees, and positive 20 degrees or negative 20 degrees, depending on if you want forward or you want reverse. So that's the charge pump thrown in there to do some more activities. So that sound fair? This is what the charge pump can do for you. Anything you want it to do. So I can control my swash plate angle now with a charge pump instead of the older systems that were physically a mechanical lever connected right to the swash plate angle. That sound fair? Okay. So there's a couple more points I can pull out on that, and I should understand on that. And that is a couple more points. I've got this to consider. Or I have this to consider. And by this and this, what have I really created here? The pump is infinitely variable. the motor could have an option that I am either 10 degrees or I am 20 degrees. This pump is infinitely variable. The motor is either swash plate angle A or swash plate angle B. Displacement as referred to as minimum or maximum. So this happens to be maximum displacement and B is obviously and should be minimum displacement. So what does that mean to you? Pumps only produce flow, and I'm going to take flow to try and do some mechanical work. And really, that is to say that work is no more than trying to, this is an actuator. I'm trying to rotate something as well as develop some force. So I can do one or the other. This is variable displacement actuator, and as such, this variable displacement actuator, maximum displacement is referred to visually as a cylinder that might look like this. And I'm going to put some oil into that to try and do some work with it, versus a cylinder that might look like this one, to try and do some work with it. And the relative understanding is, based off of this surface area on this, is the same as the displacement on this. The more the displacement on this, the more oil I have to displace to move that cylinder, the more my force goes up. But because I have to displace so much, my speed is down comparably. In other words, as far as the speed on this side is concerned, rotating wise, the maximum RPM that I would get out of this on this maximum displacement, I might be able to get from 0 RPM all the way up to maybe 100 RPM on A. If I was on displacement B, now, oh really? Takes me no time at all to move that. So if I was on B, I might be able to go all the way from 0 to 300 RPM. Infinitely variable versus the 0 to 100 RPM. So now I have a smaller displacement, so I can get an overall output speed much faster. But nothing's free. And by nothing's free, something had to be sacrificed. Speed was increased. What I could capably get out of that would be much faster than this one. But I had to sacrifice something. By the surface area in here, I had to sacrifice force. So one of these might be the rabbit, one of these might be the turtle. So here we go with rabbit, and this might be my turtle version. Examples of multiple displacements. Now I have a 2-speed motor. 2 distinctive different speed ranges based off of displacement, variable displacement motor. Yes, it's infinitely variable, but my output is very different. In B, I got a lot more speed, so I can get to that gravel pile faster. The problem is, when I run into the gravel pile, I only have enough rotational force to only put the bucket halfway into the pile, and then my drive wheels actually spin out. By spin out? No, they stall out. They won't spin out. They don't have enough force to spin out. They go into the pile and the wheels just stop. So if I had an automated system that might recognize that, it would actually, with 2-speed capabilities, it could go touring across a job site, go into the pile and stall out, recognize it stalled out, and then I could build in an automated system that would automatically take that swash plate angle and increase it up to here, and then all of a sudden I got a bigger displacement and my wheels can start digging a hole into the ground, and I push the bucket right full and it's flowing out the side, and life is good with that. Away I go. So that could be a 2-speed option, which could be automated, or again, as far as that is concerned, this is just a swash plate angle, which, guess who supplies the swash plate angle? That's our charge pump. So our swash plate angle, whatever is controlling this swash plate angle, it's nothing more than another actuator controlling that swash plate angle. Again, that's nothing more than coming from my DCV, which is really coming out of my charge pump circuit. So the charge pump can now, right, if I had a 2-speed motor, I can use that for controlling the swash plate angle on my 2-speed motor, as well as the infinitely variable swash plate angle on the pump. So that's where the charge pump comes in. And there's a couple things that we need to keep in mind here. And by a couple things to keep in mind, what I've drawn out and give you examples of is enough to drive this. It's enough to drive one motor. Meaning, on a skid steer, I have one pump dedicated to one motor, which happens to be the right-hand side. Oh, really? One pump, one motor? No, I need 2 motors. So the reality of this is everything that you see here is enough to drive one side of an HST, closed-loop HST system in a skid steer. And therefore, the left-hand side, in this case that I've given, requires the same thing all over again. The only thing you can get by with is you can share the cooler, you can share the filtration, and you can even share the charge pump and just run. You could even share the charge pump and just run this charge pump around all the way into another loop system to feed oil into this and put, again, some isolation check balls into this system. I could do that. Not a very pretty picture, I know. But I could run more isolation check balls into it. And I could get by with just one particular charge pump. But I would certainly want to try this loop in for cooling as well. And this one would have its own flushing valve and its own tied in to the cooler. By the way, this one would need its own high pressure reliefs to protect that high pressure closed loop in either direction, because there's no way that I can put that one. Those are not going to protect here, so it must have its own high pressure reliefs. So 4 high pressure reliefs required. Why? Because I need one for forward and one for reverse on the right hand side, and I need one for forward and one for reverse on the left hand side. I need one right hand side infinitely variable or reversible flow variable pump, and I need one possibly, not always, possibly variable displacement motor for that right hand side. I also need the same for the left hand side. I need another big ass pump, sorry, pardon my French, and I need another big motor to drive this. High pressure reliefs, yeah, okay. That's the start of it. That's HST. So, customer complaint. I got 4 high pressure reliefs. I'm just going to highlight this right now. 8,000 on one side, 4,000 on the other. What's the customer's complaint now if I'm driving in forward into the gravel pile and it happens to be in maximum displacement so it can spin its wheels if it wants? But what's the real customer complaint if I take in the high pressure relief and it's broken a spring and it's only got 4,000 PSI? Here's a valve that's normally closed all the time. The only time it opens is if there's no, if I have too much resistance on the wheel. This is on, say, the right-hand side. So if I'm going into the pile, the left-hand closed loop system, it's got two high pressure reliefs and they're both sitting at 8,000, forward or reverse. And this right-hand forward is only on 4,000 PSI. So when I go into the pile with my HST system, what's gonna come out of this is the right-hand side is going to hit the pile and come up against resistance to try and push the bucket through the pile, and then it just hydraulically stalls out. It can't develop enough force because I've taken the pressure that was going to it and I've dropped it down. So the right hand wheel stalls out physically. Meanwhile, the left hand wheel just digs a hole in the ground because it's, hey, I got an 8,000 pound spring I have to overcome. And because of the displacement of the motor and that relief valve, it can develop enough rotational force that it can just spin the wheel right in the ground. So that's one of the complaints that would happen with this HST system if one spring was weak. And to be very clear, this is a normally closed valve. And to just drive a skid steer across the ground, it would track perfect. It would absolutely track perfect because it is still a normally closed valve, and to just drive across the ground might take all of a 800,000 PSI resistance just to drive it across the ground. So that valve would stay closed, and the only time you're going to actually notice something is when I physically come up against enough resistance and then the right wheel stalls out and the left one's trying to dig itself into the ground. So that's how the high pressure relief scenario problem comes into play. And I think that's good enough for about an HST system for today. Feel free to ask me questions and or throw some input in after the fact. 52 minutes worth, 53.